Turns out servers are pretty good. They're so good that Vercel decided to add them to their serverless. Wait, what? Okay, hear me out. Today's episode is going to be a little bit different. This is the first major thing Vercel has shipped since they stopped sponsoring me, but thankfully, I'm not the only one talking about how cool it is. We're going to dive into a lot of fun things here, from serverless, its strengths and weaknesses, to the core of how Node works, to a bunch of Vercel haters that are actually saying this is dope. This episode is not sponsored by Vercel in any way, shape, or form. As y'all know, we broke up. They no longer pay me at all. That said, we do have a sponsor today, so let's hear from them really quick. Concurrency is going to save you a lot of money, but you still need to make sure the right users are hitting your stuff and they're not hitting it too much. That's why Unkey exists. They make it super easy to authenticate your users of your APIs and also rate limit them. I'm going to show you just how easy by using the rest of this ad time to do it. Here I have a slow API. Slow data fetch, get, you know how APIs work. I'm going to grab the code here, straight from their docs, to set up a rate limiter. Paste, done. I have strict type rules, so I have to put that there. And then to use it, we just copy this part. I already have the identifier. It's the IP address. Paste that there, switch identifier to IP. And now a user with a given IP address can only hit this endpoint 2 times per 30 seconds. How do I know? I'll show you. Go to it, refresh a whole bunch. Works fine. But now we're getting rate limited. That easy. Oh, by the way, almost forgot to mention, entirely open source, so you can pay them or you can host it yourself. I'm just going to pay them because it's way easier. Thank you to Unkey for sponsoring today's video. Now, before we get back to me yapping, I think it's important to contextualize how awesome this is by hearing from some people who are a little more skeptical, to say the least.
Hey, I'm AJ. I'm an AWS hero and a staff engineer at Datadog. Theo isn't just blindly shilling for Vercel here. Shipping multi-concurrency to Lambda is a remarkable accomplishment, and it's the type of thing that I've been asking AWS to build into Lambda for a number of years now. I'm happy to see that Vercel did it, and I hope this puts more pressure on the AWS team to innovate and build more features like this into Lambda, driving the cost down for this product for the rest of us. It's a good thing. We should be happy about it.
Hey everyone, Dax here. So I've been known to not say the most positive things about Vercel, we'll put it that way. But when they do something cool, I don't mind saying it. This new multi-concurrency thing that they have shipped is pretty cool. I've been hoping that AWS would add this as an option for a very long time. Vercel beat them to it, which means their customers get to access this first. And I think it's going to have some pretty cool impacts on the more serious workloads that are running there.
Serverless servers. Efficient serverless Node.js with in-function concurrency. This is the actual feature here, in-function concurrency. In order to understand why this is cool, it's pretty important to understand how serverless works. I have a really awesome video called The Truth About Serverless that should probably be out already. It's not, sadly, but keep an eye out for that. It should come out very, very soon. If you're struggling to keep up with this, make sure you watch that video when it drops because it'll give you a lot more context on how we got to serverless in the first place. And this is almost like a fun set of steps back, not like backwards as in it's getting worse, but back as in we are learning from things that work better in other environments and trying to bridge the gaps between all of them. Also, thank you for getting this far without bullying me for my voice. I was at a Y Combinator event yesterday and had a lot of talking to do. Building a compute layer that is highly optimized for interactive workloads, server rendering, and APIs. We're sharing a first look at the new version of Vercel functions with support for in-function concurrency that brings the best of servers to serverless functions. We've been testing this new version with customers, and we're seeing a 20 to 50% reduction in compute usage and respective cost reduction without latency impact. It's a serverless product optimized specifically for interactive workloads such as server rendering of web pages, APIs, and AI applications. Vercel functions continue to offer native Node support with accelerated cold start performance based on V8 bytecode and instance pre-warming for production workloads. That's all the other fun things they want to brag about that they built. Some of them are pretty cool, not going to lie, but we're focused almost entirely on the in-function concurrency. History of serverless for interactive workloads. Thankful they established this history a little bit so you guys can hopefully keep up with the benefits. When AWS Lambda introduced functions as a service, it revolutionized batch workloads by mapping one function instance to one invocation. So what that means is previously, if I had a Node server running in a VPS and 100 users were making requests, those 100 users would be hitting the same computer processing everything with just one instance of Node. So you can almost think of it like if you run npm run start, it's running on your computer. Now 100 people are hitting that instance of Node.js from that npm start. With Lambda, you have an npm start per request effectively, where every user who's going to your website, if there isn't a Lambda already going that they can hit, which often there wouldn't be, then a new box was spun up, your code was moved to it, npm run start was run, the user would make their request, get whatever response they're supposed to get, and then the connection would be over. That server would sit around for half a second to 2 seconds, seeing if another request comes in. And if it does, it'll take that, solve it, send it out. But the important detail here is that there's never more than one request at a time on a given Lambda. This is awesome because it means if you do crazy CPU-bound stuff or you have something that's really fast for some users but really slow for others, Lambda and serverless effectively allow you to not worry about the amount of allocation and how slow or fast things are. This is a huge benefit because scale is no longer a thing you have to be as considerate of when you're building this way, both up and down, but it also comes at the cost of not getting those concurrency benefits. An important thing to think about is all the stuff that you can do while you're waiting for another request. If user A comes in and user A is requesting data that requires a trip to the database, while you're waiting for that trip to the database, user B can come in and do something before user A gets their response. With Lambda, user A and user B are hitting different computers, so you're paying for the time it takes for both separately. And that's the key thing here. More than anything, it's going to be cost. There are some other benefits we'll talk about. But with a server, you're only billed on how much time the server is up for. With serverless, every single request has its own machine, so you're billed for the time being spent on every single one of those requests. This gets really bad if you have to wait for something for a while. Like let's say you're doing an AI gen tool and it takes 20 seconds to respond. Now, when a user makes a request, this Lambda spins up, receives the request, goes to this third-party service, waits 20 seconds that you are paying for every second of, comes back, sends it to the user. With servers, when that request is going, you could be doing other things for other users, so that 20-second window isn't just being paid for one single user. Hopefully you're starting to see why this might be cool. As Malta says here, this model struggles with interactive dynamic workloads, where single user requests are tied to one function instance, which sits idle when the compute is waiting for the backend to respond. These inefficiencies become even more apparent with AI models and other I/O-heavy applications that can take seconds to respond. With in-function concurrency, Vercel functions break away from Lambda's one-to-one mapping from invocation to compute, leading to substantial efficiency wins. And this is an important detail, I/O heavy. In case you don't already know this about Node, it actually handles I/O really, really well. Literally every reputable technical person from the Node.js core contributors to the PM from GCP Cloud Run, all the way down to Dax, agree that this is a good feature from Vercel. You'd think people would take the hint before piling on to the losing side of the argument. Love this. Kudos to Vercel. This is one of the biggest blockers for many non-front-end use cases. Like Firebase functions and Cloud Run functions, Vercel enables per-instance concurrency for Node functions. Guess what? Customers see drastic cost reductions. Mild shock. You're wasting money if you use a runtime that only offers single concurrency. Node was built for high concurrency. See a case study we published in 2019 on the topic. This piece here, Node was built for high concurrency. This is a thing I want to emphasize. This talk is incredibly underrated, and I think it's important for the conversation we're about to have. This is the original reveal of Node.js, the first time Ryan Dahl shared it with the world. And there are some bold statements in here that I think are important for us to understand.
We're doing it wrong. Everything, the way that we're thinking about doing I/O really makes things difficult. So writing servers and writing any sort of application is difficult because of how we're doing I/O.
Bold statement. I/O is things that aren't just the logic that you wrote. Be it you're calling your database, you're reading a file, you're updating Redis, you're doing anything that exists outside of your logic, your code, and your direct language. Those I/O bounds often would cause programs to halt and wait and not be able to do other things. And Ryan Dahl's unique angle here might surprise some of y'all, because obviously we love to stereotype Node as being slow, but for some things it's actually really, really good.
So a lot of web applications have such line of code, like you query a database and then you return a result and then you use the result. And so the question is, what is your web framework doing while this line of code is running?
Really good question. What is your web framework doing while you are waiting for the result from this db.query call?
So in many cases, you're not doing anything at all. You're just sitting there while the database is waiting to respond. The point is that you can't just wait for it to respond. There's a big difference between what happens inside your CPU, inside your memory, and what happens when you go to something outside of that. If you go to a disk, or if you go to a network, if you have to do a TCP connection to a different server, even if it's in your same hosting center, then you're talking about millions of clock cycles instead of hundreds of clock cycles or tens of clock cycles. So obviously better software can do better than just wait for the database to respond.
If you find this interesting, highly recommend checking out the whole thing. It'll be linked in the description, but this is the part that I think is really important to understand what Node does really well. Great comment. The fact that this man is nervous gives me the biggest dose of imposter syndrome ever. To be fair, what he was doing here is terrifying. Like, absolutely terrifying. Like saying, hey, I think JavaScript might be one of the best languages for the server. Like, even now it's controversial. So not surprising, it's scary, but yes. And yeah, both JSConf and Ryan Dahl have evolved a lot since then. Because JSConf was still just like a front-end conversation.
That's where you call a function and it connects to some server and returns something from that server as if no time has passed. And then you're going to use the result beyond that. This somehow either requires blocking the entire process, or you're going to have some sort of threading system. Maybe it's coroutines, but it's probably going to require multiple execution stacks. But you could have the code like this, where you make the query to the database, and instead of waiting for the response inside that function, you give it a callback.
Important note here, promises weren't really a thing yet. So this is what we would do. We would pass callback functions. So you have your db.query call, which is very high resolution here. Select whatever, comma, function results. And it would call this results function after this is done. What's really awesome here is that you don't have to wait for the db.query to finish before you could start doing other things for other users. It is a huge change. Huge change when previously you would just wait until it was done and not do anything until it was over. Or you'd have to spit out to the operating system to do things like with threads in the OS. The event loop is a really cool concept, and bringing that to the server had a lot of power for a lot of these things.
In one form or another. When this happens, your execution can run right through that statement, make that request, and continue doing other things. When the request comes back, millions and millions of clock cycles later, you can execute the callback.
That is the important detail more than anything else here. Millions upon millions of clock cycles later. There's all this time the CPU is spending waiting for this data to come back, where it's doing nothing. Millions of cycles where it could be computing other stuff. Money that you're spending on your server sitting there doing nothing. And that sucks.
No machinery involved in this. All you need is a pointer to that callback. So this is how we need to do I/O. If you want very fast, high concurrency servers, you have to design them like this.
I know a slide like this is controversial. 11 years ago, this is how I/O should be done. Saying this is how inputs and outputs should be handled all over the internet, with an example in JavaScript when JS was not a server-side language yet, was bold. But it turns out in many ways, he was very, very right. Now we need to talk a bit about what actually shipped here with Vercel's serverless servers. But first, we have to understand why this was necessary. Remember before when we said there were those millions of CPU cycles that were being thrown away because we were waiting for that request to come back? Well, if every request is on its own computer, those millions of wasted cycles are happening on Lambda the way they were before Node in the first place. Because when you're waiting for that stuff to come back, another user isn't having their stuff done. The Lambda isn't doing anything when it waits because other users are on other Lambdas. They're on other servers. Because of that, one of the biggest benefits of Node, which is the I/O and async model, is just not being used really when you use it with serverless. Node's built-in concurrency, which is really, really powerful, is being opted out of in favor of serverless being your concurrency layer. This is effectively like, where is your concurrency happening? And with Node, your concurrency is actually pretty easy to make happen on the server. With Lambda, that's your concurrency model, but that means you don't get the benefits from Node, and you're spending a lot more money and wasting a lot more cycles that Node could have optimized. Hopefully you're starting to see why this might be really cool. The journey to in-function concurrency. In 2022, we released Next 13 with streaming for React server-side rendering. Vercel's serverless functions, previously a relatively thin wrapper around AWS Lambda, faced limitations as Lambda didn't support streaming. Big deal. It's cool that they do now, but at the time, the thought of supporting streaming in Lambda was just not something AWS really cared about. So the solution Vercel came up with, as I think they show here, maybe they don't show it directly, kind of here, yeah. They had a service, the function invocation service, that was running on their own edge that would make the Lambda startup or find the right one. It would connect via a socket to send data back to this other instance, this other service, whatever it is. I think it was a Cloudflare worker at some point, might have been CloudFront, not sure which. But this would be an edge function of some form that invocates and triggers the Lambda, makes a connection to it, and then that connection sends data back to this additional layer that can then stream it to the users directly. Really, really powerful. But what this means is, instead of the traditional model with Lambda, where you have a, how do I even put it? This is different from the traditional Lambda model where you have effectively a routing table that says this URL points to this JavaScript, and then it will dump that JavaScript into a Lambda and execute it and send a response based on what URL you went to. Now they have their own layer that will interpret the URL, figure out where it's supposed to go, see if a Lambda is already running, make a connection to that Lambda, stream data back, maybe it hits a cache along the way, all those types of things. They built a layer to control how the Lambda is used rather than just using the Lambda. This is why they can do cool things like partial pre-rendering. Our idea was to have the function open up a secure TCP socket back to the original function invocation service and use that socket to stream back responses, even if the actual Lambda invocation doesn't support streaming. Another important detail with Lambda is they kind of had two models. One was an on-request invocation model, where the user requesting something is the thing that triggers the Lambda. The other model is the manual invocation model, where you have your own backend or service that is manually triggering a Lambda via an API when it wants it. And that's what they moved to by putting a layer in front. But once they got this deployed, they had a realization. A bidirectional stream to all functions could enable much, much more. In particular, like giving them additional work. Oh boy. Part 2, Rust-powered functions. Yes, Rust is actually involved here. With the idea in mind, we got a prototype to work, but there were a few things we needed to address first. Keeping the behavior consistent with the expectation of serverless environments was tough. To solve this, we shifted focus to the function runtime and began rewriting Vercel functions runtime in Rust. The rewrite itself unlocks several performance improvements and better debuggability of the system for users. You can essentially think of the runtime as the ultra-stable in-function hypervisor that orchestrates the workload even if a single function invocation gets in trouble. This is effectively their wrapper around V8 and everything else that can run in your Lambda to make sure the right code is running and nothing's gone wrong, and then you can spin it up as fast as possible and execute it reasonably well. Rust can take this 1W. But now where things get fun is when you pull it all together. Finally, we have all the building blocks in place to start shipping in-function concurrency to Vercel functions for real. The new architecture looks like this. You have the edge routing, which is figuring out where you're supposed to go. The function load balancer, which makes sure you're not overwhelming whatever is triggering these functions. The function invocation service, which figures out what code needs to run and where it can possibly run. And this service keeps track of what Lambdas are up that have the code that you need. And if there's already one up that has the code you need, even if it's already doing something else for another user, now it can send that request there. So any one instance of a Lambda function can now serve multiple requests. So if you have a Lambda that's currently blocked on I/O, it's doing a database request, it's doing some 20-second long fetch from some AI service, those types of things, it can serve other users' requests at the same time. As traffic reaches our data center, it's routed through a function load balancer to the function invocation service. This service manages connections ranging from a single function instance up to 100,000 instances per function. It ensures traffic is routed to a function invocation service likely to have in-flight invocations for the desired function instances. When an invocation request arrives, the service checks for available instances, and if one exists, it forwards the request to it. This is what's cool. This helps at basically any scale. If you have hundreds of thousands of functions running, or if you have one running, It takes less time for a user to start getting a response, and you're spending less money because you have less instances running. This is just one of the many examples of something fun that gets solved here. Let's say I have my database. We're going to do a real example and say that this database is on Heroku, because this is a real problem that I had when I first started using Vercel. So we have our database. In the old world, we would also have our server. The server and the database would form a connection, and that connection would just stay. Once the server spins up, it connects to the database, and it keeps that connection. Now, if we have a whole bunch of users all making requests, user makes a request, user makes a request, maybe we finally get the response for that one, this user's request comes in, we finish the response for this one, then we finish the response for this one. Bit of a mess, but you get the idea. This one server is taking all of the requests that all the users are making and using this one single database connection to get the data for all of those. Let's say suddenly you have millions of users. Maybe you've just spun up a few more servers. So you have 3 servers spun up to handle the load balancing. And now we have the database connected to all 3 of these. These arrows should have been one way, not 2 ways. I'm too lazy to change it. You get the idea. The point I'm trying to make here is a set of users, if not all of your users, would connect to a single server, and that one server would have one database connection that it could serve many users, many requests with. Where things start to fall apart is when each user gets its own server. So with serverless and Lambda, it looks more like this. Each request from each user gets its own server, and that server needs to make its own request and its own connection to the database when it makes that request. There's a couple issues here. First off, making these connections isn't free. These can take sometimes seconds to form, which can get really slow really quick. This is a huge part of why cold starts suck. It's not because the Lambda takes forever to spin up. It's because the connection to the database can sometimes be very slow to make. On top of that, a lot of databases, like the example I gave of Heroku, were very limited for how many connections they could manage at once. On Heroku, there was a limit of 10 on the free tier. Even though you could do a shitload of traffic through the database, you could only make 10 connections to it, which meant if you were using Vercel and Heroku back in the day, even just in dev mode, like when you load a page, if it makes 5 queries, all of those queries get rerun once. You just hit 11 requests on one page load, and those might all be spun up on different servers. You might have just hit your database concurrency limit just refreshing your page in dev mode, which is insane. It's awful. And the experience I had trying to get Heroku and things like it to work was terrible. Have you ever heard the term serverless databases and thought, oh, that's stupid, what do they mean? This is what they mean. What they mean is that this pile of connections no longer matters because you can make the connections faster, and once the connection is made, you don't have to worry about how many of them there are. Now imagine if your Lambda server that got spun up because of that request could also serve a few more of them. That you could have this short-lived server serve a few requests from a few users instead of just one from one user. Now you're starting to reuse these connections much more aggressively. That is huge. One of the many things that this changes is the absurd level of need for a heavy pooling system or third-party layer to manage all of your connections for your database. Really cool stuff. Let's go back to the article because they have a lot more interesting things to say. Efficiency gains. Our private beta customers have reported significant efficiency improvements, with some seeing up to a 50% reduction in compute usage. I saw one that was even higher in like the 80s, but I don't know how reproducible that is, so I don't want to cite it as like a definitive example. This means fewer gigabyte hours billed for the same workload with no code changes. Results will vary depending on your backend communication and traffic volume, as the efficiency gains from concurrency apply best when a minimum number of requests is met. What they're saying here is y'all and your zero-user apps are not going to see a big benefit here. And I might self-own in a bit and show you guys how much and little we're seeing the benefits ourselves. But I also know some companies are seeing huge benefits because they got a lot of users. Here's how these gains are achieved. Remember, in the traditional serverless model, each invocation is tied to a single function instance. So traditional model, we have one function invocation. It does some compute. It makes a request. It does nothing. And then when the request is responded to, it does some compute and then sends the response to the user. So think of this like a user goes to my page. I start generating the page. I realize, oh, I need to get some data from the database. We wait until we get the data back, and then we generate the rest of the result. Node would allow you to do other things during this idle window. But since the function only has one user's request in it, it can't. And if you had a second thing from a second user, they could both be idling at the same time. You could have 2 servers doing nothing at the same time and a third server doing a bunch of work, and there was no way to share all of that. Vercel's new system, however, allows a single instance to handle multiple invocations by utilizing idle time spent waiting on backend responses. This is the key I'm trying to drive home here. So now, when the compute gets done for the first request, and now it is idling, waiting for that API request to come in, function 2 can start doing its compute in the same Lambda, wait for its API response. While it's waiting for that API response, send function 1's response to the user, and do the same for function 2 when it's done. Within function concurrency, a single function instance can utilize already available compute for new function calls. For example, let's say a request takes 100 milliseconds, with 50 milliseconds spent on computation and 50 milliseconds waiting for a backend response. The old model, the 2 requests would require a total of 200 milliseconds of compute time. With the new model, those 2 requests could be handled by 1 invocation, reducing the actual compute time to around 100 milliseconds. Huge. I'm already seeing some people talking about other solutions. The 2 things that are worth talking about are Cloudflare, as well as the new low latency runtime that Bot Cooper brought up here. If you're not familiar, some employees at Amazon have been on the side working on a new runtime for JavaScript that allows the cold starts to be better on AWS. What it doesn't allow for is for multiple functions to be resolved in that instance at once. What Cloudflare does with workers is very important to understand. Cloudflare workers are isolating at a slightly different layer. So if we are looking here for how Lambda works, each of these boxes is its own computer that runs Node.js. And inside any one of these, even once you do this change, it's only running one npm start. And that single npm start is serving multiple requests from your users at the same time. So all 3 of these requests are hitting the same web server that your code spun up, and that web server is running on a single box. The way that this works on Cloudflare is a little bit different. Cloudflare workers don't bill on idle time. When you're waiting for a response from something, you don't get charged money for that on workers. But how can they do that? That's insanely expensive, right? Well, it's not that expensive when all of these servers aren't actually servers, when all of these are instances of a V8 isolate. And V8, which is the JavaScript runtime, is the big box on top. So you have a V8 server that is creating these isolated little layers inside of it for your code and for other customers' code. You have one server that's running code for a bunch of different people at the same time, and it's able to, when your code is waiting, resolve someone else's request in an isolate in the same V8 instance, because it's all leading into the power of the event loop. When one user's request is blocking because it's waiting for something, it's not blocking that computer's ability to do other stuff, so it can go do other stuff for other users, which allows Cloudflare to not charge you when that is going on. But that's because all the different users are resolving their requests at the same time on the same servers. It's possible that hundreds of different developers are serving thousands of different applications at the same time on the same server using the Cloudflare workerd V8 isolate model. But with this, each server is still yours when it is running. When your code is done and it's past that 2-second window or so before it idles, in that time, it's yours. And once the time is passed, it can go to someone else. But there's never one server running multiple people's code at the same time. So the low latency runtime by AWS won't benefit this at all, because when your compute isn't running, it still has to keep the server up waiting. It's also worth noting that Cloudflare runs their own service. They run their own infra, which is part of why they can do things like this, where Vercel is running on top of AWS. So they're kind of bound by that stuff. Also worth noting that because this all lives in V8, you don't get access to a lot of things you have in Node. Like you don't get access to file system. You can't read and write files in the file system when you're using Cloudflare, because you don't have access to those things, because theoretically, if a lot of people are using the box at the same time, there's no guarantee that you're not writing things that would screw with someone else's invocation. You also have to rely on V8 to be your memory isolation layer to make sure different processes don't screw with each other. Thankfully, V8's really good at this, but it's still not a guarantee. It also means you can't reuse things the same way, where you can't reuse a connection in the V8 isolate model. So this thing where you have 3 requests being resolved by the same thing at the same time isn't really possible, because you can't persist things between stuff like that. Like once the worker is done with its work, it goes off, because I guess the question to ask is, where is the concurrency happening? With a traditional VPS, the concurrency happens entirely in Node. And if you need more concurrency, you have to build up a load balancer in multiple servers to manage that for you. With Lambda, the concurrency happens entirely through the different server instances. With the new Vercel concurrency model, the Lambdas can be a concurrency model on the outside, and you can have these additional concurrency layers inside of any one of these functions. With Cloudflare, the concurrency model is the individual processes spun up in V8. But the way to think about this is, how do these different models handle concurrency? And if you understand where the concurrency exists in all of these models, I think the rest makes a lot of sense from there. Now that you hopefully understand the difference in these different concurrency models, you can understand how bold but also true this statement is. Fulfilling the Node.js dream on serverless. Node.js was created to handle asynchronous I/O concurrently. While existing functions as a service products could take advantage of this in the context of a single invocation, they often don't have the opportunity to use all of the available CPU. So to be clear what this means, taking advantage of it in a single invocation, is if I have like 3 database requests, I can trigger all of them. I can do other work for that user while those 3 DB requests are coming in. And then once all are in, I can wrap up the work. But if I don't have any more compute to do for that user, I can't do it for another user on that box. So I'm just paying for idle clock time. But with in-function concurrency, Vercel functions take full advantage of Node's concurrency capabilities. As an example, whenever a function is stalled, waiting for a backend to respond, it can handle a second request with the available CPU immediately. Respectively, the compute time is utilized rather than sitting idle, leading to substantial efficiency gains. I wanted to showcase these efficiency gains with actual applications I've deployed, but I can already see the 0 user comments. I don't care. I'll defend myself. Here is the results after I turned this on for Ping last night. You already know, Ping is our video call app we went through Y Combinator with. It's making it easier for people to do live content collaborations directly in OBS. We've been used by everybody from Linus Tech Tips to Ironmost to Elgato. It's a really cool product that we're super proud of. However, the amount of actual requests that users are making once they've connected to our WebRTC system and to our WebSocket system is relatively low. Because of that, even if we have a lot of users concurrently on the service, they're not making a lot of requests. So we've not actually seen any meaningful savings on this service in the 16-ish hours I've had it on for. I did turn it on slightly earlier for upload thing though. And also am seeing very little here. But of note is how few gigabyte hours we're actually consuming, because most of our APIs now aren't on Vercel anymore. We moved a lot of our APIs off, not because Vercel is terrible for it, but because we built a new ingest server. If we were still using Vercel for our APIs, this would be killer. But it's just a matter of how much compute is even being done on the platform. We also have the fun thing worth considering, which is that this upload thing deployment on Vercel is just our dashboard. And once users have things set up in upload thing, they don't check the dashboard a whole lot. But that's why we're not seeing much here. So in the example that Made on Verse used in the thumbnail here, they saved a ton, literally right around 50%, because their compute took forever. An individual request could take seconds, if not tens of seconds for a user, and in that time they could serve other requests. Here's another fun example where this user, who was doing 3,000 plus hours of compute, was able to save significant amounts, as high as 35%, just by hitting that one switch. Really, really cool. But it does require that you're consuming a lot of hours. The more hours you're consuming, the more this saves. And for those who complain a lot about Vercel's costs, I understand. But they could have just done this quietly and not told people and just taken this win for themselves. But they're not. They're forwarding the savings on to you as the user. They spent all of this time building this thing that AWS didn't even have the balls to build. And they're just handing you the savings. It's kind of cool. Talk all the crap you want. There's a lot of things I'll be talking crap about soon. By the way, the how to not go broke on Vercel video coming very soon. And I'm quite excited for that one. But yeah, this is dope, whether or not you like Vercel. Had a fun discovery as I was filming that video. Turns out I wasn't seeing any concurrency at all. Not because I had so few users like I thought it honestly might be, but because I hadn't done a new deploy and it was nowhere near clear enough. Lee called it out. Here are the results. We've only had it running for a few hours now, but even now we're starting to see some savings. And if I change this from last 24 hours to last hour, there's an actual percentage savings happening here, sometimes as high as 25%. And as I mentioned in the video, our utilization and the actual amount of time that our compute runs for is relatively low. So to even see a 20% savings is surprising and pretty cool. And if we go to Round, which is our video call app, not seeing massive savings immediately here either, but when there are enough requests, it very quickly spikes up. So I can comfortably say everyone will have some amount of savings here. I do not think we would, and we're starting to. And if it turns out the savings end up being much bigger after a few days, I'll be sure to put an update in the comments, so keep an eye out for that. Speed of software that runs on a server, then it's not serverless. That is, okay. We did it, boys. We found the actual dumbest attempt at a community note of all time. The suggested note was written by someone who doesn't understand what the term serverless means. Yep. Hilarious. A+. Back to the article. Trade-offs for the current implementation. During the beta phase, we're limiting the maximum number of concurrent invocations dispatched to a single function instance. We'll slowly increase these limits over the duration of the beta period so that we can monitor trade-offs between efficiency and latency. While we've seen performance gains with all private beta customers, the mechanism may increase latency for purely CPU-bound workloads. So what this means is if the concurrency is running, but you're not spending much time on I/O, you're spending time doing things like, I don't know, generating a really, really complex page, which is a blocking task if it's running in JavaScript. If your JavaScript code itself is the thing that's taking a while, not the I/O that is blocking it, that time spent could block the next user's request. So if we go back up here, this compute is blocking. So if this function for this user started slightly earlier, it wouldn't be able to actually start doing work until function 1 stopped doing compute and started waiting for something that it was fetching over the network. So if you're spending more time generating the page than you are waiting for data from other places, this might actually hurt your performance. But again, it's where is the concurrency happening? If your code takes very little time to run, but you're waiting a long time on things externally, like the example of the 20-second waiting for an AI service, this is going to benefit you immensely. If your responses from your database are really, really fast already, like you're using PlanetScale or Terso or things like that, where you don't benefit as much from the pooled connections, you don't have to wait that long time to make the connection, and you're getting responses in maybe 300 milliseconds or less at times, the benefit gets much smaller because you're spending an equal amount of time doing compute and waiting, and the likelihood another user's function can run in a way that's actually faster for them and cheaper for you is lower. But it really depends on how much of your time is spent calculating versus waiting. And if more of the time is spent waiting, you'll feel much more of the benefit. But if you've already optimized your services to spend very, very little time waiting, this won't benefit you as much. They also are working on detecting this. We expect our detection of unhelpful concurrency to substantially improve during the beta period, ensuring that it's only used in the right situations. Finally, this mechanism inherently changes that a single node process handles multiple invocations concurrently. As mentioned above, this is really how Node is typically being run in production. Therefore, while this is technically a backwards incompatible change, as well as an opt-in change, we expect the vast majority of workloads to work under the new semantics. Important detail here. If you have something in your code like a memory leak, it's actually pretty fine to deal with memory leaks and lambdas as long as they're not aggressive, because it will stop running before the memory leak gets bad. And we even had memory leaks in some of our code that we didn't notice until we moved off of serverless because the server never ran long enough to hit the leak. But also if you're doing things like you're using Lambda and you temporarily write a file at the system that's like current user info, but now 3 requests are coming in, they're all rewriting the same file with the same name, it can break. But if you wrote your code in a way that is stateless, so to speak, which is how I usually recommend writing logical code for servers, let the state live somewhere else like your database or Redis, and let the server do its work. If you're using that model, this is a thing you can just turn on for no risk. But if you're utilizing the fact that every request is its own machine, be it by letting memory leak and not caring, being by throwing and killing the whole server in different scenarios, be it writing files to things that are using fixed names, those types of things aren't viable when you're running one server with lots of requests. That all said, you're hopefully not doing that. And I can't imagine many are, but I'm very curious to see over time how many users actually run into bugs because of this. One important detail that I think people are missing, especially when I look at things like that awful community note, is that this is still serverless. While the new architecture substantially increases the efficiency of Vercel functions, it changes absolutely nothing about their serverless nature. Vercel functions continue to do the following. They scale automatically, they never go into maintenance mode, all maintenance is handled automatically with no impact on users or availability, and they transparently ship security updates for operating system and runtime stuff without any downtime or work for you. Because again, It is true serverless. So at any point, requests, when they're resolved, the server can die and the next request can go to a new server. You can have a bunch of servers running the old thing with 10 seconds left and start spinning up the new server for new users going forward. You can swap between all these things, one-click rollbacks, because in the end, all that's changing is which code is being executed by the Lambda. And this is why things like preview deployments can be free, because each preview deployment doesn't need a server running for it. You have to wait for it to spin up. I can go to a pull request from a year and a half ago on an old project and click the preview deploy link, and it will still work because Vercel is able to take advantage of the fact that when no one's going to it, it costs them no money. This is the Verse example that I mentioned before. After Verse launched their internet bedroom website, traffic surged from hundreds of thousands to over 10 million visitors. At its peak, 15,000 users were online concurrently, creating a flood of requests, as well as potential idle time. This made it an ideal candidate for the new optimization. With early access to in-function concurrency, the Vercel functions cut gigabyte hours and reduced costs by over 50% through automated, smarter usage of compute during idle times. Here's a comment from the team. Many of our API endpoints were lightweight and involved external requests, resulting in idle compute time. By leveraging in-function concurrency, we were able to share compute resources between requests, cutting costs by over half with zero code changes. Pretty cool. You can try it out today. As long as you're a pro or enterprise customer, it's a checkbox. You can go hit in the settings. Pretty cool stuff. They have a cool acknowledgement section at the end here where they call out that Google Cloud Run was a pioneer in concurrent, fully managed containers. Their public preview function product has similar concurrency properties. Zooming out from Node, products like Deploy, Cloudflare Workers, and our own Edge functions have similarly innovated on concurrent invocations for serverless-like compute. But as I mentioned before, with all of those, it's because they're living in some runtime that is doing the isolation. It's not happening because of an external layer. But that's part of why this is so cool. It's a huge change in how we think about concurrency in serverless workloads. Cloud Run did it before, but I'll be honest, no one thinks about Google Cloud, so it barely mattered. It's cool they called it out at least, but yeah. Vercel aren't the only ones talking about this though. Boba, who's a friend of the channel and author of many incredible blog posts in this general space, wrote something about it, and I can't not read his post. He rushed this out just for us, so huge shout out to Boba. Give him a follow if you haven't. Let's take a quick look. Intended or not, this tweet garnered a lot of attention and led to countless meme responses thanks to a seemingly nonsensical phrase, serverless server. On one hand, that's just how social media works. People like to have fun and farm engagement. On the other hand, many have strong opinions on Vercel and its products, so any Vercel news is bound to generate some chatters. Regardless, it's a bit unfortunate that a lot of people seem to have stopped at poking fun of the phrase and skipped the linked blog post explaining the new feature. Here's a summary of what they added. We hopefully just summarized all of this, but it's cool that all of these people who have had positive and negative things to say about Vercel, at least the smart ones, are coming together in droves to say, no, wait, y'all, this is actually really cool. This is clearly a big efficiency gain, and many Vercel function users are already seeing a significant reduction in compute cost. But to me, this new feature is also a telltale of how React's new full-stack architecture vision needs more than a framework, and how a product like Vercel's is almost inevitable. Okay, you have my attention. The cornerstone of the new React architecture is that a React app consists of both a server part and a client part. React app developers are encouraged to keep data management to the server part and keep the client part lean. This change has at least two consequences: more traffic to the server and more async calls on the server. Kind of. Big kind of here. The thing I want to call out is there's a lot of instances where with the new model, you're not actually getting more traffic to the server in terms of the number of requests. I'm going to give a weird example. We're going to go to twitch.tv, and I'm going to go to the network tab. I'm also going to add a filter for just what is effectively requests that are JSON, like API requests. That is 40 plus requests, especially at least ones to GQL. All the GQL ones, these are all requests to a Twitch server to get data that this page needs. So on this one page load, we made at least 11 API requests just to load the page one time. The cool thing with the new React model is it's much easier to make a powerful, dynamic application where only one request is done. That one request can stream in additional data, but you only have to authenticate the user once. You only have to check their headers once. You only have to connect to the database once. You only have to do a lot of things one time, and you're only doing one request on the page load now. Where with here, we load the page, and now we're making a ton of requests that have to repeat a ton of work. So In one hand, we are moving work to the server, but on the other hand, when we do that, we're able to meaningfully reduce the amount of invocations of a bunch of work have to be done as a user loads a page. So it's a two-sided thing. Dev makes a fair point here, which is that when you're navigating around, you're saving on server requests. When you're making small changes with RSCs, you need to re-render the whole thing instead of refetching small amounts of data. So there are cases where you're increasing server work. Kind of. The other thing here is if you just have an outer shell that does the requests for data, and from that point forward, everything's a client component, the payload you're sending from the server is just a dump of all of the data. This is how it works in things like Remix. This is how it worked in Pages Router too, but it's way easier to assemble it and build it in. If you're sending server components down to the client instead of client JavaScript, you do have to refetch the markup as well, but often that ends up being smaller than the giant JSON payloads being sent. Like again, if we go to Twitch and we look at the network tab, I want you all to see how absurd some of these JQL payload responses are. Look at this shit. Like, what? This is just one of them. There is a ton of stuff like this in all of these requests, and they are long and they have a ton of data and they sometimes take a ton of time. So sure, but on everything I do on this site, it's the same deal. So it's checks and balances. In the end, if you're not using Relay, you're not doing anywhere near the most optimal data solution, but server components get you a lot closer. So I don't fully agree that this inherently means more traffic to the server. It does probably mean more async calls on the server, though. I'll cave there. Think of a scenario where the app is mutating some server data and updating a view based on the latest data. Previously, this could be handled mostly on the client side by directly calling external API endpoints and handling view updates. In the new React architecture, this would generally go through the server part, tasked to both fetch server data and render components using the data. That is fair. Once you're interacting with the page and triggering updates, you generate the whole page again. But this also helps prevent a bunch of other classes of bugs and allows you to, like, here's another common use case. You update your username or you update your display name on Twitch. Now it has to invalidate like 15 things, which fires a bunch of queries, which then trigger additional queries. Sure, you don't have to regenerate the whole page, but that tends to not be that expensive. And by doing it this way, you avoid a lot of those stale state issues that are very common in single page apps, and you reduce a lot of repeated compute for things like re-authenticating for each of those requests. So it's checks and balances. I don't think it's fair to say one does more requests than the other. They both have different traffic patterns. And I would argue most of the time, the new server component patterns end up being more optimal in terms of the amount of traffic actually running on your servers. The contrast is more stark in the case of Next.js. App Router, which is the de facto standard implementation of the full stack React architecture, has added support for not only server-side React, but also for nested routes, which encourage developers to build apps with more granular routes to mirror their data requirements. When combined with app routers, every route starts from server approach, we likely get more server traffic where the whole server tree gets reconstructed and all relevant data fetching needs to be resolved. More traffic to the server and more async calls on the server. Fair. Next mitigates this with its sophisticated beat me to it. I was about to bring up the caching, but they called that out already. The sophisticated caching as well as the component rendering allows you to avoid a lot of these unnecessary things, but this can only go so far for dynamic apps that frequently update their data in views. To be truly scalable, it needs support from an infrastructure for distributed deployment, and that's where Vercel enters. So how does the story relate to the serverless servers and in-function concurrency? Deploying Next on Vercel means using Vercel functions to serve traffic. For the app router days, I suspect the cost of one instance per invocation setups wasn't so ostensible, but the increased server needs of app router brought attention to the limitation. Also fair, I saw a lot of people who would use Next.js on Vercel as just a slightly nicer Create React app, and they would still hit APIs on the client side that had nothing to do with Vercel for a lot of their data. I even see companies building AI tools that generate an Express backend and a Next frontend, which makes me want to die. Given how so many apps deployed on Vercel are Next apps and the growing popularity of App Router, I suspect that the dramatic reduction in cost from in-function concurrencies are from serving large Next apps on App Router. No. Because large Next apps are spending a lot more time doing compute, not waiting on I/O. The customers that will be saving the most money by far are people who are using really slow databases or customers that are using things like an external AI service that takes 20 plus seconds to respond. Those are the biggest winners here by a lot. If you have a big app that's rendering a ton of React components, this won't benefit you as much. But if you're firing off really slow API requests, that's when the benefit will really kick in. The bigger story, of course, is the increasingly strong vertical alignment between React, Next, and Vercel. No nefarious conspiracy is required for this alignment. Rather, it illustrates the challenge of React's new architecture that seeks to embrace the server-client model in a particular way. When React was client-side only, the cost of its component orientation was largely hidden. Sure, performance, but the user bore the brunt of cost in UX, and its impact on developers was often indirect at best. As React moves to the server side, the costs start to show up on bills. Covering both client and server side is a framework's job. Making it efficient seems to require support from their infra. Can this be changed, perhaps by a new approach to the full stack React? Really good article overall, but I want to emphasize that the underlying thought here of the cost of rendering these large apps and recreating the HTML isn't something this concurrency model solves. It is purely the time spent waiting for things that are happening externally. If your React code is what's slow, this doesn't benefit you. If your data requests are what's slow, this benefits you immensely. It's also of note that this benefits a lot of workflows and a lot of things that aren't just Next. I haven't confirmed this, and if Lee, you're still here, I'd love a confirmation. I'm pretty sure you can still run this on things that aren't Next. Like I could run this on SvelteKit totally fine. I could run this if I deployed Express on Vercel, probably totally fine. Not positive about that, but relatively sure. Yeah, definitely good for any SSR frameworks. Exactly. So if you're making slow API requests, this benefits you. Framework agnostic. Thank you all for the confirmation. So yes, more React devs are moving things to the server, and they're making more API requests than they're used to making, and they're now being done on a Lambda, which is blocking in a way that it wasn't on client because you're paying for those costs now. But I would argue the big difference is previously, when you were waiting for an API request to respond and it took 20 seconds, the compute that was waiting for it was the users, so you weren't paying for it. But now that your server is the thing waiting, you are paying for it unless you're serving other requests at the same time. But that's where the shift happened, is waiting shifted from the client to the server. Node shouldn't block when you wait, but Node on Lambda did block when you wait because they hoisted the concurrency layer up to the server level. Now, if the concurrency can also exist there, you get the best of both. This is a really cool solution that benefits a lot of things. It's just that the React developers were feeling it disproportionately because we're the ones building with most of these new APIs. We're the ones building these crappy AI apps. And we're the ones going all in on serverless. And many of us have not deployed on servers before. I've spent a lot of time on these things, and I've thought about this far too much. But many React devs haven't. And by solving these problems at an infra level, you can do the right thing more easily. And that's why I'm excited. This stuff is not simple, but it is really exciting. And the future that it enables is hopefully one where you don't have to think about any of this stuff at all. Let me know what you're thinking, though. And until next time, peace, nerds.